Okay, welcome everybody to today's talk. As a guest, we have Tim Palmer today from the University of Oxford. Tim Palmer did his PhD at the University of Oxford as well, under the supervision of Dennis Sharma in general relativity, but then moved to climate science, climatology, in which he worked for many years and continues to do work. He's now back at the University of Oxford as a Royal Society research professor, and he has his own group, and he has received many prizes and grants, most notably recently an advanced grant, another advanced grant from the European Research Council, and is going to present today some work which is not the main work that he's doing. It's much more foundational. He will be talking about foundational issues which will have implications both for quantum theory as such and for quantum gravity as well. The title of the talk is "What Physics Needs is not so much a quantum theory of gravity as a gravitational theory of the quantum." Please, Tim.
Thank you, Christian. It's a great pleasure and indeed honour to be here today and to give this talk. I've made the title deliberately controversial because what I want to try to propose is that maybe because of my background in general relativity, I really don't see gravity as yet another force to be brought under the control of quantum field theory as the other forces of nature. And in fact, I'm going to propose, perhaps, as I say, controversially, that the reason why we have not been, to date at least, successful in producing a theory which synthesizes quantum mechanics, or quantum physics, let's say, and gravitational physics, is because we're sort of looking in the wrong direction, so to speak. Instead of trying to fit gravity within the framework of quantum field theory, which manifestly works very well for the other forces of nature, I'm going to propose something rather more radical, which is to think of the problem the other way around. How can we make quantum physics more compatible with the basic framework which Einstein's theory of general relativity has given us? In fact, perhaps I can put it even more sort of colloquially and say that my own view is that we're sort of putting the cart before the horse in trying to formulate our theory of quantum gravity, where the horse is gravity and the cart is quantum physics. So in other words, I'm going to try to propose here that to really understand quantum physics, we need to think about how gravity might actually be the guiding principle behind quantum theory. And I've been deliberately very provocative here, because I'm not just talking about the measurement problem. So there have been Penrose, Dioschi, and others have proposed that gravity may play a role in the measurement problem. I'm going to propose something even much more sort of profound here and radical, which is that even the unitary process of unitary quantum mechanics, gravity plays a profound and essential role. Now, you know, at the face of it, there would be two perhaps immediate reactions to such a proposal. One would be that surely gravity is utterly negligible in any kind of laboratory type, or certainly during unitary evolution. Surely gravity plays a negligibly small role. That would be, I guess, a very common reaction to such a proposal. I'm going to try to. I won't convince you, but I'll try to demonstrate why, in my view, that notion may be false in a very specific technical sense. But the second objection, which is the one I want to spend most of the time talking about, is that if one takes the view that the principles of best theory of gravity, which is general relativity, should be guiding quantum physics, then we're saying that surely quantum physics has to be somehow, because it's geometric, it has to be deterministic, realistic, and above all, locally causal, because that's what general relativity is, a theory that's deterministic, realistic, and locally causal. And of course that flies immediately into headlong into the big problem of if you like, Bell's theorem, and the fact that we now have a lot of experimental evidence that physics cannot seemingly be both realistic and locally causal by all the various recent quantum entanglement experiments. Now, so I'm going to frame some of the discussion in my talk around one of the implicit assumptions that is made in the interpretation of these experiments, called measurement independence. And this quote I've got at the bottom was actually taken from one of these Nature News and Views commentaries on one of these quantum entanglement experiments. And generically, when one reads these types of papers, there's always, this point is always brought up, but then it's immediately rejected. And I guess the quantum foundations community is almost, I would say, as far as I can tell, almost universally of a voice that breaking this so-called measurement independence assumption, which could, if one could justify breaking it, would allow you to potentially then reinstate the notions of realism, determinism, and causality into quantum physics. It's generally assumed that this leads to something that is physically implausible. So the measurement independence assumption is basically saying that if one imagines a theory, so-called hidden variable theory, where particles and so on can be labeled with some variables lambda, then the probability distribution of these variables lambda should not depend on the specific types of measurements or experiments that are done at some subsequent time after, say, the particles have been created. So the technical assumption is that the probability distribution of hidden variables conditioned on the actual type of measurement that's made is just the unconditioned probability distribution. So the measurement makes no impact on the assumption. And if you break that, if you say, well, the measurement that we do, the experimenters do, does actually have somehow does constrain the probability distribution of the hidden variables, then one is led with this seeming kind of impossible to understand physical constraint, that in the way this quote of Seilinger has it, the notion that the hidden variables are somehow therefore must be manipulating the experimenter's choices of what properties they actually measure, tricking them into thinking quantum theory is correct. So this seems perfectly sensible reaction to this type of breaking this assumption. Because if you broke it, it would seem to be saying that, okay, at the moment the particle is created, it has a particular hidden variable lambda stamped on itself, let's say, and if that is conditioned on the experiment, then the particle would somehow know it's been drawn from a distribution which is being constrained by this experiment, and therefore the experimenter in the future has to perform that experiment, and that seems completely bizarre, or at least, unacceptable. And for that reason, I guess almost universally people reject this assumption, which is why the prevailing view is that quantum physics cannot be both realistic and locally causal. Now, I want to discuss this in the context of nonlinear dynamical systems theory, because I don't think it's quite as straightforward as has been made out here. And just to motivate what I want to talk about, well, obviously, so the question about whether hidden variables are manipulating experimenters' minds then, raises this question about what is free will, what freedom do experimenters have, and so on. Now, that's a thorny philosophical question that I don't wish to kind of get into to define what free will means. But I think we can all agree that if it was possible to predict ahead of time what an experimenter might choose to do, let's say, or any of us might choose to do, I mean, that would be a condition where free will was obviously somehow violated. If you could run on your laptop a program that would say exactly what I was going to do, in the next 2 hours, then manifestly I would not be free. I would somehow be constrained somehow by the algorithm that was running in the laptop. So, if it was possible to predict the future in some algorithmic sense, then clearly we experimenters would not have free will. So I want to start asking the question from a fundamental physical point of view. Why do we think it is not possible to predict what experimenters are going to do? I'm just going to focus, by the way, in much of the talk. We'll see how time goes, but just something actually very simple, where we've got an interferometer experiment where we can either measure, let's say, momentum with all the mirrors put in, or we can take out this half-silvered mirror and measure which way the particle went. So we're going from x equals 0 stands for a quantum momentum experiment, and x equals 1 stands for a quantum position experiment. So the question is, why? So these experimenters, will choose at some, let's say tomorrow, they will choose to either do this experiment or this experiment. Now, why is it not possible today to predict their choice? Well, in ordinary classical physics, we have this phenomenon of chaos, which I'm sure everyone's familiar with. That relatively simple. This is Ed Lorenz, the discoverer of these three somewhat simple nonlinear differential equations, which exhibit this property of sensitivity to initial conditions. So it's difficult to predict the future of the Lorenz equations because we have to know the initial conditions rather precisely to be able to reliably say something about the future. And if we've got errors on those initial conditions, then eventually that will lead the prediction to deviate from, let's say, the true prediction. Now, chaos is certainly a practical limit. I mean, chaos is in some sense practically, at a practical level, makes it difficult to predict the future. But actually, it doesn't stop us at a fundamental level from predicting the future, because you could always say with a chaotic system like this one that if you knew the initial conditions sufficiently well, you could actually predict as far ahead as you like. So if you said to me, I want to predict with this set of equations, 1 million time steps into the future, then I could tell you how accurately you need to know the initial state to do that. And of course, the further ahead you want to make the prediction, the more accurate you need to know the initial conditions. But in principle, there's nothing stopping you. At a fundamental level, there is nothing stopping you from predicting at any finite time ahead, as long as you know your initial conditions sufficiently well. So chaos itself actually is not a fundamental reason for not being able to predict the future. But what I want to discuss here is something which is actually quite, is a kind of intrinsic to chaos theory, which in some sense I would say, explores a deeper property of chaotic dynamics. Just to backflip a minute. I mean, this is the famous Lorenz Attractor. So if you plot, if you start with some initial condition and run it forward with these differential equations, and plot the evolution in the three-dimensional state space, or phase space, if you like, of these equations. So here are two of them. There's a third one coming out of the board. What you find is that the solution seems to settle down onto some geometric shape, which, in fact, it was Lorenz's, I think, brilliance and genius to realize that this geometry that it was asymptotically settling down onto, if you like, was a fractal. It wasn't any kind of simple Euclidean geometry, it was a fractal geometry. And here's just a blow-up of that same fractal geometry. Now, what I want to just say now is something which is in some sense a deeper property of chaos than just looking at initial uncertainty for a finite time in the future. Because at a sort of deep technical level, you could say that these attractors, these asymptotic geometries that these differential equations describe, are technically non-computable in the following sense. Suppose I wanted to note whether a particular point in this three-dimensional state space lay on the attractor. Was it a point that lay on this attractor? Then you wouldn't actually be able to decide that algorithmically. And it's simple, you can understand that quite simply, because you can imagine, for example, so this picture here has been generated by a computer integrating these differential equations. And to do that, the first thing you have to do is say, right, I'm going to represent these real number variables, x, y, and z, by some floating point real number representation on the computer with, let's say, 64 bits or something. Each x, y, and z will be represented by a 64-bit double precision floating point real number. And so, this will get something very complicated, but actually it won't be a fractal, because it'll have some inherent granularity. And it could be that your chosen point actually lies on one of these sort of 64-bit sort of these finite width trajectories. But the problem is, if you then up your numerical precision to, let's say, quadruple precision, 128 bits, then you'll find that one of these trajectories that you thought your point lay on actually will split up into yet a smaller set of trajectories. And now your point may suddenly, at this higher level of precision, lie actually in one of the gaps. So this is if one takes a transverse section through these these trajectories, you're looking actually at a Cantor set, something that has literally structure that if you zoom into just keeps repeating itself indefinitely. So any finite precision attempt to calculate whether a given point P lies on this attractor will be unreliable, because it may be at higher precision still, the point that you thought was on the attractor is no longer on the attractor. I'm just going to say, by the way, just because this is an important point, I can phrase this, what I've just said, in a finite sense, because sometimes people say to me, well, okay, but talking about fractals is a rather mathematical thing, and we should think of physics as somehow finite. Physics is not really about infinitesimals. Physics should be about finite systems. And there's a counterpart of this non-computability property which does still hold in a finite context. So let's imagine that reality was actually something finite. So let's take this 256-bit representation of these equations as truth. So in principle, then, you could decide whether P belonged to this 256-bit representation of the Lorenz Attractor. But now you ask the question: suppose I try to compute, suppose I try to ascertain whether this point lay on this attractor with a smaller precision. So I'm going to go from 256 bits, let's say, back down to 64 bits. Then the estimation with the 64-bit calculation will not be a reliable predictor of whether the point lay on the attractor at say, 256 bits. This is a property which Stephen Wolfram has called computational irreducibility for finite systems. So this is the finite counterpart of non-computability in the infinitesimal limit. So computational irreducibility is where you say a system cannot be reliably simulated with a smaller system. You cannot take a subset of that full system and reliably simulate it with a smaller system. So you need the full finite extent of the system to be able to simulate it. That's computational irreducibility. All right, I want to just point out that there is some rigorous maths behind this, which is described in a book called Complexity and Real Computation. One of the co-authors is Stephen Smale, who's one of the real sort of founding figures of these types of fractal attractor sets. And the particular theorem is called halting sets must have integral Hausdorff dimension. So halting sets are to do with things that are computable, and the thing that these fractal attractors don't have are integral Hausdorff dimensions. They have fractional Hausdorff dimensions. And I just want to, in passing almost, just point out that a person who's been very vocal about the potential role of non-computable elements in physics has been Roger Penrose. And I'll just quote a little bit from his Emperor's New Mind. Some new procedure takes over, he claims, at the quantum classical borderline, which would contain an essentially non-algorithmic element. The future would not be computable from the present, even though it might be determined by it.
Can I ask?
Yes.
Let's go back to simple harmonic oscillators.
Yes.
Chaos. But if you integrate it just step by step on a computer, and you have not a good, then the resolution that you take for your real number, pseudo-real numbers, 64 bits or whatever, will also have an effect. If you have a poor resolution and you integrate for long enough, instead of turning in a circle as we know the solution should look like, you also run away with it.
Yes.
So it has nothing to do with chaos.
Well, what I'm claiming is that I want to I'm looking at systems which have self-similar structure, because the reason why so in your case you would be able to do a kind of epsilon type of argument and say by increasing the precision sufficiently I can get as close as I like to the final exact solution. Now in this case this is not true, because for any finite representation of the trajectory, it has structure within it. It has structure within it. But anyway, let's look at one second. Right, so what I I want to try to discuss today is what physics might look like if our universe were actually a deterministic dynamical system, somewhat like this Lorenz system. So instead of 3 equations, we've got zillions of equations, but nevertheless, there is some holistic structure in its phase space on which the universe, our dynamical system, the universe, is evolving. I'm calling this I subscript U. I stands for the invariant set. The attractor is an invariant set in the sense that once you're on it forever. In the traditional, Friedman, Robertson, Walker universe, sort of closed universe, or where you've got multiple epochs which bounce from Big Bang to Big Crunch to Big Bang to Big Crunch and so on. What I'm imagining here is that in the phase space of the universe, I'm just inviting you to consider, let's say, a situation in which in the phase space of this universe, these evolving epochs actually get folded into a compact set which has a, let's say, fractal-like structure. However, I don't necessarily want to be so specific as saying that this only works for a closed universe, because, well, I guess we don't know at the moment. The universe seems to be flat, so it could be closed or it could be open, we don't know. Penrose has proposed a kind of an alternate idea for a multi-epoch universe based on conformal rescale. So the idea is that the universe in a particular epoch, although it is open and expanding forever, it asymptotically becomes massless, his claim is, and that can be conformally rescaled back to a Big Bang of the next epoch. So again, without going into any details, because it's not necessary for this talk, we just imagine a series of universes. Time is now going up in this direction, time is along here, time is going along here, time is going up here. And again, we imagine in the state space of the universe, this is somehow being, the evolution is occurring in a compact, fractal-like set. So now I want to come back to more kind of quantum, thinking about quantum mechanics, and propose something which would be super deterministic and in the kind of conventional sense would be regarded as preposterous for the reasons of the quote, of Seilinger's quote at the beginning of the talk. But let me just run through this. So I'm going to imagine, so let's start down here. Here's a particle which has been created at some time t0, and it's going to be measured at some later time t1. So t0 is an early time, t1 is a late time. And what I'm showing here are trajectories of the universe, some of which lie on my supposed invariant set, and the solid ones, and the dashed ones don't. And what I'm going to propose here is something very simple, that we can think of a hidden variable. Actually, it doesn't need to be hidden for the reasons I'll talk about, but let's say that we've got some variable which is somehow stamped on the stamped on the particle, if you like. And it's drawn from one of two distributions, lambda subscript x equals 0, which is our momentum experiment, and lambda subscript x equals 1, which is our position experiment. And I imagine these lambdas are disjoint, and they're different from each other, they're not the same. So here's a particle on an actual universe, the universe which lies on this invariant set. Its lambda belongs to lambda 0 precisely because at this time t1 the experiment x equals 0, the momentum experiment, is going to be performed on it. This is a universe, on the other hand, where the opposite experiment is done, the x equals 1 experiment, and as a result, the corresponding particle on this trajectory, on this state space trajectory, or this history, if you like, would have lambda drawn from lambda x equals 1, which is different from lambda x equals 0. Now, these dashed lines correspond to universes which don't lie on the invariant set. Now, I'm going to give you a reason why quantum physics might well be described by these conditions. But at the moment, you just accept I'm just describing. I'm not justifying it. I'm just describing what these lines mean. So here are two dashed lines which by construction don't lie on this invariant set. And these correspond to universes where there's a kind of inconsistency between the lambda and the experiment. So here's one where the lambda for the particle is being drawn from capital lambda 1, which is the position type of experiment. But actually what happened was a momentum experiment. And similarly, this one has been drawn from the lambda naught sample, but a position measurement has been done. Now you could think of these as, for example, representing going from an actual, what I'm supposing here to be an actual world, to a counterfactual world, where I have, for example, going from here to here is equivalent to taking this particle with the lambda drawn from lambda naught, and whereas in reality I would do a momentum experiment, in this off the attractor type of world, then this corresponds to one where I've kept the lambda fixed but changed the experiment to a position experiment. So this is like a counterfactual world. If I say what would have happened had I taken this particular particle with this particular lambda and done a position experiment, whereas in reality I did a momentum experiment, then I'm claiming in this model that takes me off this invariant set. Now, as I say, later in the talk I'll try and show how quantum physics, or the formalism of quantum mechanics can be made consistent with this idea. But let's just, if you can follow what I'm saying, just take this as a sort of description of what these lines are. Now, at face value, this would fall into all this sort of objection that people raise. Let's call it Zeilinger's objection, because this says, okay, the particle says to itself, what lambda have I got? Okay, the answer is my lambda has been drawn from capital lambda naught. That means that at this time t naught, there is no option other than the experiment x equals naught is going to be performed. Because if I did an x equals 1 experiment with this lambda, I'm off the invariant set. So this seems completely crazy, because this means that the experimenters at this time are forced, they have no option, according to this description, but to do the x equals naught experiment. So the Zeilinger objection would certainly hold at face value. But I want to now throw in this question about non-computability, which at the face of it sounds just a rather technical question, but I believe there's something philosophically and conceptually important. It provides a conceptually important constraint. Let's suppose that it was actually fundamentally unknowable at t equals t naught whether lambda belonged to lambda 0 or capital lambda 1. Because in a sense, to know whether lambda belongs to lambda 0, we have to predict whether x equals naught, the experiment x equals naught will be performed, or the experiment x equals 1. Now, I'm sure you're thinking at the moment that, okay, if I say that, knowing whether lambda belongs to lambda naught or lambda 1 is uncomputable, it makes, and you'll probably think, well, that's just technical, but surely in some sense, either, the fact that lambda does belong to lambda naught, it must either cause the experimenter to perform x equals naught, or maybe somehow there's some retrocausal effect where the fact that the experimenter did choose x equals naught somehow retrocausally made lambda belong to lambda naught. But I'm going to argue in the next slide and the next two slides that this notion of causality or retrocausality, in the case where this is not a computable function or not a computable variable, is actually a misunderstanding, is misusing the meaning of the word causality. And I want to introduce this concept with a rather more, let's say, practical world example. So we'll sort of move away from particles and quantum mechanics and just think about babies. Okay, so here's a baby. It's certainly true that babies are either born male, well, okay. Get into complications here, but let's assume for the sake of that babies are either born male or female, okay? So we can partition, so a baby either belongs to a certain male, and we can find out. It's easy to determine whether a baby is a male baby or a female baby by a number of ways. We could take a blood sample and look at the DNA and the chromosomes and such like, and there are more obvious ways, I suppose, of determining that. So, okay, that's straightforward. But let's look at something which is not quite so straightforward. Suppose, well, it is true, it is a true statement that at birth, a baby will either belong to the set, which I'm going to call set L, of babies who in later life fall in love. Or, if they don't belong to that set, they're going to belong to the set not L of babies who in later life do not fall in love. So we can associate any particular baby with belonging to this set of male or female, or indeed we can say that it is true that this set, they belong to either the set L or not L of babies who in later life do or don't fall in love. So what's the difference between these two sets, pairs of sets? Well, clearly a key difference is this is knowable at birth. We can do tests in a number of different ways to determine whether they belong to M or F, but there aren't any tests which you can do to determine whether they belong to L or not L. Well, okay, you might say, let's get a big supercomputer and run it into the future and try and predict whether it belongs to L or not L, but you know, that's impossible because certainly chaos theory will stop you ever being able to predict that. So in a sense, you could say that this, you know, there is no kind of observable at near the time of birth to say whether the baby belongs to L or not L, but there are manifestly observables that can determine whether they belong to M or F. On the other hand, it's clearly preposterous to assert that, you know, the fact that a baby belongs to either L or not L somehow causes the subsequent adult to fall or not fall in love. That would be a daft thing to say. And it also would be ridiculous thing to say that, or preposterous thing to say, that falling in love actually retrocausally led the baby to be classified as belonging to L or not L. In other words, yes.
It's preposterous, but that's my solution.
Okay, well, I'm going to propose something different because I don't think that is the right solution. And I believe it's preposterous to say these things because so when you belong to proposing whether you belong to L or not L is testable by experiment. So one can associate that proposition that the baby belongs to M, let's say, with an actual experiment that can be done in space-time, you know, at the time of birth or near the time of birth. So there is a mapping, if you like, to some of a statement which is there's a mapping to a practical experiment which can be done in space-time.
But
On the other hand,
assuming determinism or even hyperdeterminism. At birth, it's just the future is open. You don't know. It's not determined.
Let's assume it's determined. No, I'm sorry. Okay, let's assume it is determined. Let's assume the world is determined. Let's assume, in principle, I'm basing everything I want to talk about on determinism. So let's assume we live in a deterministic world. Nevertheless, you would not be able to determine in practice whether the baby belonged to L or not L. Because of the reasons I said at the beginning, it would be you could not find a computer big enough, nor measure initial conditions accurately enough to be able to calculate. This is an analogy for what I want to use in a more fundamental level, but on a practical level, it would be impossible. There's no experiment you could do, nor any prediction you could do at the time t0 to determine the truth or falsehood of the baby belonging to L. So in other words, what I'm claiming is that, in fact, these kind of define points in state space, but they don't define points in space-time. By saying it's a point in state space, I can say, these are points which, under the action of these supposedly deterministic evolution equations, will lead this point to lie in the part of state space where humans are in love, let's say. And being in love is something testable, let's say. I mean, more or less we can assume that being in love is testable experimentally. So this corresponds, stating that Alice and Bob, let's say, are in love, is something we can test experimentally. But saying that the baby belongs to the class L of human beings that in later life will fall in love, this does not correspond to any event in space-time at the time the baby has been born. So that for me is, and the point about state space is that there is no Lorentzian metric on state space. The Lorentzian metric is a metric on space-time. So we can't take points in state space and say that they're causally somehow are or aren't causally related or retrocausally related. It's a meaningless concept in state space to talk about causality. Causality only makes sense if we can map these statements in state space into events in space-time. And we can if it was M and F here, because we can do the experiment of testing the DNA, let's say testing the 23rd chromosome. But we can't do it for this type of proposition, which is essentially a non-computable proposition. All right, so that's what I want to try to get over here. This notion where we have a mathematically defined statement, but one that is not amenable either to experiment or to any finite computation at this time t0 when the particle has been created, means that we can think of these as points in state space, but we can't think of them, they don't relate to events in space-time. So to say that lambda belongs to lambda naught somehow causes x equals naught, or conversely that x equals naught retro causes lambda to belong to lambda naught, is just, in my view, completely physically meaningless in my statement. This raises a question which I don't want to get into any technicality over, but it's an important question in my view, which is that because a lot of my ideas evolve around the structure of state space, and this notion of, let's say, fractal structure. So it's certainly the case that state space does not have any Lorentzian structure. That's a space-time property of space-time. So you could ask, actually, and it's a good question to ask, what is the appropriate metric to use in talking about distances between points in state space? So, for example, here, if I took a point here on this trajectory, which lies on my fractal set, and a point here, which by construction doesn't lie on this fractal set, then you could ask the question, what is the distance between these 2 points? Now, it turns out that this is not an immediately obvious question to ask, because in mathematics, and in particular in number theory, there are 2 completely contrasting notions of distance. In fact, there are only 2. These exhaust all possible what are called norm-induced metrics in number theory. And both these metrics have correspondences in geometry. So the one metric that we're all used to in physics is the Euclidean metric. And the Euclidean metric is the natural metric to describe distances on Euclidean geometries, the line, the circle, the sphere, cube, and so on and so forth. But in number theory, there's a second type of metric called the p-adic metric. There's a whole class of number theory called p-adic numbers, which turn out to be extremely useful. You know, Andrew Wiles's proof of Fermat's theorem made essential use of some deep number theoretic properties of the so-called p-adic numbers. But the only point I'm not going to discuss any of that here, except to say that p-adic numbers and the p-adic metric is to fractal geometry as the Euclidean numbers and Euclidean metric is to Euclidean geometry. And in particular, in this p-adic metric, it turns out that the distance between this point on this invariant set and this point off the invariant set is actually is more distant than the distance between this point, which is on the set, and this point, which is on the set. So the distance between this point and this point is relatively small compared with the distance between this point and this point off the set. So you could say that trying to perturb your state off the invariant set actually corresponds in the p-adic sense to a large amplitude perturbation. So if you want a metric which kind of respects the primacy of this fractal geometry, then p-adic metrics do that. I just had this slide up to show how important metrics are. And in fact, I don't know whether I'll get to, in fact I won't. What time did I start?
Sometime after 6, I think.
Okay, so I'm actually not going to get as far in my talk as I wanted to, but I need to speed up a bit. But if I were to get to Bell's theorem, which I'm not going to get to, I realise now, it turns out there's an analogy which is quite close to what I want to talk about. The point about this is metrics are very important, and we can be fooled if we use the wrong metric to look at something. So this is the classic Penrose impossible triangle, which looks, indeed impossible to understand in a two-dimensional Euclidean metric. But it's easy to understand if we view it from a three-dimensional perspective. So this is the impossible triangle. You just look at it from over here, and it looks like that. The point is that we thought, our intuition was that this point C and C prime are somehow close together. But actually, they're not close together, they're far apart. And this analogy is actually quite precise when we were to examine the Bell theorem in more detail from this p-adic perspective. So I just want to spend the last few minutes, because I realise I'm out of time, pretty much. And then I'll skip over a load of slides and come to the conclusion. I just want to say something about how these ideas might link to quantum mechanics, and in particular to Hilbert vectors. And the first point to make is that Hilbert vectors certainly can describe classical systems under some uncertainty. So if I put this dice in a box where I couldn't see it, and I rolled the dice, and I said, what's the state of the dice? then I could represent that, you know, where let's say 6 represents this one, where the 6 is face upwards, and 1, 2, 3, 4, 5 represent states where the other numbers are upwards. I can represent the uncertain state of the dice when the dice is inside the box that I can't see by this Hilbert vector. The crucial thing for it to correspond to something classical is that these amplitudes squared must give me rational numbers. Now, I want to do something very similar in this description of this invariant set. So I will be deviating from the Lorenz Attractor by having some structure which is more relevant to quantum theory. So, for example, a trajectory in state space, if you zoom into it, the fractal structure will reveal itself by a kind of helical structure where the small scale trajectories wrap around the coarse scale trajectory. And at a finer scale still, there'll be fine scale trajectories wrapping around these other ones. I think I'll move to this. So can we, the question, sorry, I didn't need to say something else. And then the idea is these trajectories undergo some period of instability, which we can think of as parts of the system interacting with other parts of the system in what we would call decoherence, and forming discrete clusters, which I can label A or not A. And then I'm going to use the language of Hilbert vectors, but now complex Hilbert vectors, to describe this type of uncertain structure. Now, I don't have time to, so the first point is just following the remark about the dice. If I want to interpret this in a probabilistic way, then these amplitudes squared had better be rational. So cos squared theta over 2 is proportional to cos theta. So that if these squared amplitudes are rational, then cos theta better be rational. Now these complex phases can be given a probabilistic interpretation. They're associated with this helical structure for these fine scale trajectories. But basically, to have this probabilistic interpretation, then these phase angles phi must themselves be rational multiples of pi, or rational multiples of 2 pi. It just reflects the fact there are, if you like, just a finite number of these helical structures on a coarse-grained trajectory. I don't have time to go into this in detail. But now, this is a kind of an important point now, that suppose we take the Hilbert vector for my momentum measurement. And I asked the counterfactual question, what would have happened had instead I did a position measurement by taking away that second half silvered mirror. Now we know in quantum theory, the way to do that is to transform this Hilbert vector with a unitary transformation, which will give me something, which will take this into something like this. So I've got amplitudes where they've got these cosine factors, and they get transformed into a Hilbert vector where there's a complex phase angle, phi. Now, if you remember from my previous slide, if I want this to have a probabilistic representation, then cos phi had better be rational. If I want this to have a probabilistic representation, then phi itself is a fraction of 2.
Why should probabilities be rational numbers?
Because I want to interpret probability in the simplest, frequentist description. So you have a sample space of events, a fraction of which, let's take the dice, a fraction of which will be labelled 6, and a fraction of which will be labelled, let's say, not 6. And for the to have that frequentist probabilistic description, then the probabilities have to be rational numbers, because the number of events where the event occurred divided by the total sample space, and that's finite.
The total sample is finite, yes?
Yes. So I'm assuming a finite frequentist sample here. The point I want to make here is that the condition that cosine phi is rational and the condition that phi is rational is almost certainly incompatible from number theory. So there's a theorem which the earliest reference I can find is 1956, maybe it was known before that, I'm not sure, which says that if phi is rational, then there are only 5 exceptions where cosine phi is also rational, which is basically where cosine phi equals 0 plus or minus a half or plus or minus 1. Now, in practice, you would never be able to set up an experiment where, for example, cosine phi was precisely 0. At the very least, unshieldable gravitational waves would prevent that from ever happening. So you have this situation where, with this finite representation of Hilbert vectors, there is a fundamental incompatibility between these two types of representation. So, in a nutshell, what you've got here is a number theoretic expression of what is essentially the uncertainty principle. That if you have a particular particle with a particular lambda where, let's say, a momentum measurement has been done, so lambda equals lambda naught. Now, if cosine phi is rational, then if you keep that lambda fixed and now try to do a position measurement where you require phi over 2 pi to be rational, then if cosine phi is rational, phi over 2 pi can't be rational. And you have this precise non-computability condition because there is no finite computation which will tell you whether cosine phi rather than phi over 2 pi is rational. I'm going to skip over, unfortunately, what I wanted to talk about because there's run out of time, just to do with the Bell theorem. I'm just going to finish the 2 slides, and we can talk about Bell afterwards. And it comes really back to the point. I want to try to make the case that, in fact, there is a way to reconcile the violation of the Bell inequality without violating realism or causality, local causality, with an extension of these ideas of non-computability and fractal invariant sets. If I had another half an hour, I would be able to talk about this in more detail. I just want to finish by coming back to my original proposal about the importance of gravity in unitary quantum physics. Because basically, the crucial point in all of this is to say that states of reality, states of physical reality, this is the basic postulate, lie on this special fractal attractor where there are gaps, there are places where no states of physical reality exist. And these existence of these gaps are the crucial part needed to negate the Bell theorem. So the question then is, well, what causes these gaps? What causes this fractal structure to occur? Now, in something like Lorenz 63, it's a rather phenomenological process of dissipation. Now, that would not be a reasonable thing to propose as in a theory of fundamental physics. But here I want to draw on something which again, Roger Penrose has promoted a lot, which is essentially an interpretation of the black hole no-hair theorem, which I'll put in a slightly more general way, that at final space-time singularities, like black hole singularities, there's a kind of collapse of phase space. So this is from one of his books, where he's proposing a kind of collapse in phase space, which would act exactly. So this means that phase space velocities are convergent in this region of phase space. And this would be exactly equivalent to the kind of dissipative representation of dissipation in something like Lorenz 63. Now, this is my claim then, that this is why I'm claiming we should be thinking about a gravitational theory of the quantum, because by making use of this interpretation of the black hole no-hair theorem, we can justify this type of fractal structure for this invariant set geometry with these gaps in that is needed to negate the Bell theorem in the sense of allowing a theory which does not have to violate either realism or local causality. And my claim is that gravity actually is playing both a vital and in some sense a large role during unitary evolution. But here I need to stress this word large is in this p-adic sense, because any perturbation which takes you off the invariant set into a gap is necessarily a p-adically large perturbation. So in this p-adic sense, gravity is really playing a large role, I would claim, during unitary evolution. I think I have not time to describe that. And I've not time to describe general relativity from this perspective. But I just want to conclude, although I didn't get to Bell's theorem, these ideas can be applied to Bell's theorem, and my belief is that if we introduce some of these ideas from nonlinear dynamical systems, which introduce this notion of non-computability, then in fact we have a route to evade the apparent restriction of local realism. And that this then could be the basis of turning the problem round, and asking not about the quantum theory of gravity, but rather a gravitational theory of the quantum. So I think finish
Okay, maybe we should start with a question from Chicago. Do you have any questions?
Can you hear me okay?
Yes?
Okay. There's a sort of question of clarification I wanted to go to. I'm kind of confused about exactly what that lambda zero set is. So could you say a bit more about that?
Well,
Because in the way you put it in the first place, it sort of looks like it's all ones that go to every point in state space that ends up at x equals 0. But that's not right, because some of them end up at x equals 1.
yes. Okay. Well, let's put it this way. My motivation for using that language of lambdas is really because I want to connect with this measurement independence assumption in the proof of the Bell theorem. So the Bell theorem, as it's normally stated, says that the violation of the Bell inequalities either means you have to abandon realism, you have to abandon local causality, or you have to abandon this measurement independence criteria. And that's defined. The measurement independence is defined in terms of hidden variables. So what I'm trying to do is formulate my if you like, approach in terms of these. Thank you. I'm trying to interpret my formulation of these fractal invariant sets in the language of hidden variable theory. I have to say it's not actually. It is slightly contrived, but I have to do it in order to make contact, because that's what people ask me. So how are you violating Bell inequality? So I say I'm violating it because I'm violating measurement independence. So as I say, I imagine lambda is some kind of variable which relates to the particular particle that's been created, and I'm saying that and in principle, it's a variable which determines the state after measurement, the state of the particle after measurement. In other words, whether when you do momentum measurement, whether it's detected by one detector or the other detector, or when you do position measurement, whether it's detected by one detector or the other detector. But but the key point is it's drawn from a distribution which itself depends on whether the momentum measurement is done or the position measurement is done. So it's explicitly, violates measurement independence. So it's a variable which in the normal way would determine whether the outcome of the experiment. But the capital lambda is a distribution which will be different depending on whether the measurement is position or momentum. And what I'm saying is that is, that would be rejected out of hand in the normal way, because it seems to imply that, that lambda, at the moment the particle is created, is basically determining what measurement will be done. Because if it's drawn from the lambda naught distribution, then only the x equals naught measurement can be performed, and if it's drawn from the lambda 1 distribution, then only the x equals 1 measurement can be performed. But what I'm saying is that this interpretation is not justified, or the objection to the violation of measurement independence is not justified if the criterion that lambda belongs to lambda naught at time t naught has no correspondence in either an experiment that can be performed or any computation that can be made with a finite computational system, which is a subset of the whole universe. If that's not possible, then all you can do is state that lambda belongs to lambda naught is a sort of statement in state space which has no correspondence to anything in space-time. And because of that, you can't, infer that lambda belonging to lambda naught somehow causes the experimenter to perform x equals naught, or conversely that the experimenter doing x equals naught retrocausally causes lambda to belong to lambda naught. Because my claim is that causality is a property of space-time. It's a property of the Lorentzian metric. The Lorentzian metric exists in space-time. It does not exist in state space. So properties of systems which can only be defined in state space and have no correspondence to observables in space-time are not subject to these constraints of causality, because causality is a meaningless concept for relating different parts of state space. Does that make any sense or not?
No, I think I understand, but I think that sounds like it agrees with how I understood the general argument, but there was something specific about the way you set it up that I'm kind of confused about. Because it seems like enough for that argument that it's just a fractal, whether it's in lambda 0 or in lambda 1. But that wasn't the way you put it. It would seem to be fractal whether it was in an invariant set or not in an invariant set. So I was just very confused by the ones that are in lambda 0 but not in the I sub u. Or what the point about the being in I sub u or not was.
Well, the basic postulate, all this is sort of predicated on, is that the universe. I'm trying to. So the issue is, can we interpret physics deterministically? Can we go back to good old-fashioned determinism? Not necessarily classical physics, but at least deterministic physics. So this is an attempt to row back towards a more deterministic world. Everything is determined. There's nothing undetermined or stochastic or anything like that. But that the universe as a whole is deterministically evolving precisely on this special fractal subset of its state space. Now that means that by construction, by definition if you like, points of physical reality are those which lie on this invariant set, and points which lie off it do not correspond to points of physical reality. And what I was claiming was that a typical kind of counterfactual experiment that people often posit when they're thinking about these types of quantum experiments is to say, okay, I did an experiment where the particle, where I measured the momentum of the particle, what would I have seen had I measured the position of that particle? And what I'm saying is that in this picture, an experiment where you actually measured the momentum of the particle would correspond, since by construction it's an experiment that actually occurred, then by construction the corresponding state in state space would lie, the state of the universe would lie on this invariant set. But the counterfactual world, where you keep lambda fixed at its lambda naught value, but change the experiment now to an x equal 1 experiment, that by construction lies off the invariant set, and hence it's not by construction an element of physical reality. And what I'm saying is, in quantum theory, you can give, or at least in the language of Hilbert vectors, you can get this real neat by using the number theoretic properties of trigonometric functions, and it works out wonderfully well that the momentum experiments are ones where the cosine of the angle has to be rational, and the position experiments are one where the angle itself has to be rational multiple of pi. And these are number theoretically incompatible. So if you take so that would be a manifestation of this moving off the invariant set.
Yes, that answered it perfectly. I see what you were doing. Thank you. I'm going to make one more comment though, which is about the sex assignments at birth.
Oh yes, please, yes. Yeah.
Something like 1 in 1,000, 2,000, it's really hard to do. So, I guess I didn't agree with that.
So I missed that 1 in 1,000, what was that?
That was a very idealized assumption, like it's binary.
Oh, okay. Yeah, I mean, let's make it let's think of something else. So the baby buys a red. Let's say red is an unambiguous color. Maybe you'll disagree with that. Let's say that the baby buys a red car as an adult. So you can classify them as belonging to red or not red, according to whether they buy a red car or they don't buy a red car. So that would be.
The sex was the ambiguous.
Yes.
Oh, the sex was ambiguous. Oh yeah. I realised as soon as I started talking about sex that was okay. Fine. I give in. You win.
I have a brief follow-up on the first answer you gave to Nick. So does that mean that the other counterfactual world, as it were, with where you have I forgot whether the subscripts, which one was 0 and 1.
Yeah.
You keep the same particle, but you do the other measurement.
Yes, that's right.
That is not sort of intrinsically a physically impossible world. No, it's a world that's inaccessible from the first one.
That's right.
As far as the first one's concerned, it's not.
Yes, you have to say, given that it's sort of given that the actual world is something,
right,
then this other experiment lies off it. Now, of course, you can't say ahead of time which one.
Of course.
And the other thing I want to say is not all counterfactual types of experiments will necessarily lie off this fractal set. It's not that, I mean, if you had, this is, if you just had a single limit cycle, then any perturbation would lie off that limit cycle. And it's not like that. There are actually an uncountable, this is one of the strange things about fractal. I mean, there'd be an uncountable number of points in any neighborhood which lie on this invariant set in any neighborhood. But nevertheless, there are these big gaps. And if I had time, it's basically the Bell theorem is exactly the same thing. To prove that your theory, satisfies the Bell inequality was, well, maybe I can just, okay. I mean, you have these three in the standard, the original Bell inequality. You have these three correlations with angle orientations A and B, and then B and C. A and B, B and C, and then A and C. You have the three of them together. And what I show is exactly the same thing. That if A and B and C are kind of realizable, they correspond to experiments on the invariant set, then the third correlation, let's say A and C, whatever it was, won't be. So any two, and that's why that triangle is actually quite a good analogy, because it's sort of saying you can get any two of the vertices close, points on the two vertices close together, but you can't get that third one close. And it doesn't matter which two or three you work.
Okay. Questions, comments, objections?
Long enough.
Would you mind saying something about GR you couldn't get to now?
Oh, I'd love to, yeah.
Yeah, cool. Yeah.
But then I'd have to show my slide again.
Yeah, would you be able to show something?
Whilst this,
So you could just, yeah, right here, yeah.
oh, so I'm getting the wrong way. Talk about all sorts of things. Just to say one thing before I come on to that. I had this little, I don't know if you remember it, a little picture of a trajectory where there were kind of finer scale trajectories circling around it. So there's a kind of helical geometry, so there's a periodic geometry associated with these things. And my claim is that the de Broglie, kind of like E equals h bar omega, is a kind of manifestation of how that helical geometry is determining the energy of particles on any one of those geometries. So there's something about the geometry in the neighborhood of a particular trajectory which is giving properties. A little bit like the geodesic principle in general relativity. You know, the inertial properties of a test particle on a geodesic in space-time are kind of determined by the space-time geometry in the neighborhood of that geodesic. So, all right. So, with that as background, so what I want to try to imagine is how would I generalize general relativity, and what would be the consequences of that? To make it kind of consistent with that idea that somehow it's that the geometry of space-time, in our space-time, is somehow influenced by neighboring structure in the state space of this invariant set. So that's the concept. So here's space-time, and here's the equations of GR. So I'm just going to rewrite the equations of GR trivially by integrating over imagine some sort of transverse section here through state space. This is now state space. So this is this is the universe which has some space-time m naught. And this is an integral. Okay, if I want to be technical now, this would be there. So these fractal sets have measures. There's a well-defined measure called the Haar measure. So I can actually define an integral on a transverse section through space through state space. Now, but if I put a delta function there, then all it's going to do is pick out the energy momentum at m naught, my target space-time. So I get back the equations of GR, and I can write that delta function as some distribution with a finite kernel, but take the limit n tends to infinity. Okay. But now what I want to do is that leads then to an obvious way to generalize GR to be consistent with this principle, which is that don't let n go to infinity, but let n be some large but finite fractal parameter. So this now, in this generalized general relativity, by the way, in GR, the Einstein tensor is an inviolate quantity. I mean, nobody who doesn't studies GR would want to tinker with the Einstein tensor. It's just a beautiful thing. But the energy momentum tensor is kind of it's a bit of a flaky turn of terms on the right-hand side of the equation. Nobody knows quite what it is. So this is what I'm doing. I'm playing with the right-hand side. I'm keeping the Einstein tensor absolutely fixed. But now what I've got is an integral with this finite kernel. So what you could think, what would that mean physically? So it's saying, for example, that the Einstein tensor in our space-time is somehow feeling energy momentum from the neighboring space-times in state space. Well, isn't that exactly what dark matter is, for example? Isn't that, I mean, dark matter seems to be something which you know, affects the Einstein tensor, but you know, we can't detect it from anything hot matter. So that would be one thing. Another thing would be this, and you know, this is of course what quantum gravity is supposed to do. Because this is now a finite kernel, if you imagine a collapsing space, you know, something collapsing into a black hole, you've got this term now which is smearing out over these neighboring, smearing out energy momentum over neighboring spacetimes and state space. So my claim is that, I mean, I don't know because I haven't done the calculation, but my guess is that would also prevent a singularity from forming, which is one of the reasons people believe it's important to have. Just one point I missed, well, excuse me, I lost it. Okay. No, that's fine. Let me just, I didn't really talk about this very much, but I don't know if people are familiar with the concept of a singular limit. Something Michael Berry, a physicist Michael Berry, emphasized a lot, that a good example is viscosity in a fluid. You know, we have the viscous Navier-Stokes equations which describe reality. You can set viscosity to 0 and you get the Euler equation, so the inviscid Euler equation, just ordinary classical fluid mechanics. But in a well-defined sense, the properties of a viscous fluid do not go smoothly to the inviscid limit. And the classic example is aeroplanes. If you only need an infinitesimal amount of viscosity to make an aeroplane fly. But if you set it strictly to 0, you never get any lift because the boundary condition fundamentally changes from a no slip to a slip condition. So the behavior of fluids in the inviscid limit is actually not the smooth limit of behavior in a viscous fluid as the viscosity goes to 0. It's a singular limit. And there are many examples of singular limits. And if you were to ask me, you know, how does the Schrödinger equation and stuff like that emerge out of my theory, it emerges as a singular limit. It's something where this fractal parameter, unless you set it precisely to infinity, you get the quantum theory. But the thing about this behavior is that this actually is on the gravitational side, is a completely smooth limit. This goes smoothly to the delta function. So that's my claim, is that this again is a kind of a point that invariant set theory is much more compatible with general relativity than it is with quantum theory, which is again why I believe that we should be looking at the synthesis of quantum physics and gravitational physics much more from the gravitational side than from the quantum side.
So maybe one comment and one question.
Yes.
So first the comment. The comment is that actually to derive quantum non-locality, violation of some inequality, not necessarily the CHSH, and actually not the CHSH, you don't need full measurement independence. For instance, if the lambda would determine the measurements that Alice is going to perform, but influence it by, let's say, making it 99% probable that it is measurement 0, with a small probability that it's also the alternative measurement, you can still derive quantum non-locality. You have to violate some overall inequalities and be more complex inequalities. So the comment is that you really need this hyperdeterminism. So it has really be that the lambda determines fully everything for the future, not just influence the future probabilistically. Now, if you go to these limits that it's really hyperdeterministic, as you showed, then you can indeed, with a local Weidel model, get above this local bound of 2 for CHSH. But you could also go above the 2 square root of 2 of the Thielson bound and actually go to the algebraic maxima. You can go to 4. So now that you have explained that you can go above 2, you still have to explain us why we cannot go above 2 square root of 2, isn't it?
I mean, this theory would predict experimentally exactly the same correlation as quantum theory, because it's based on these. It's essentially based on these complex Hilbert vectors. So the correlations, just as the probability was cosine squared theta over 2, so the correlation between entangled particles would be minus cosine of the relative orientation of the measurements. So it would predict, from this point of view, exactly and only the violation as is produced by quantum theory itself. So what happened? Well, again, I need to show some slides to kind of, but I don't know whether you want me to do this or not. I can try and just go through it very, very briefly and see if this makes any sense or not. Oops, one again. The slides I prepared are just the original Bell inequality because it's simpler, I think, than the CHSH.
Should we look at all the experiments? Because the original experiment inequality cannot be right.
Yeah. Well, perhaps I should put experimentally in quotes or something like that. But the point is, if you want
the inequality in the modern sense, there is an additional assumption in addition to locality. You need perfect anti-correlation.
I guess what I wanted to point out here was that, and this will be true for the CHSH, that each correlation is done on a separate set of separate sub-ensemble of particles, and in particular, because of experimental finite experimental precision, what you actually end up studying are correlations between orientations where these orientations are not precisely the orientations in the original Bell inequality, but they're approximate.
That is deeply wrong. I mean, in Bell inequality, the input is just an integer, or it's even a bit, 0 or 1. And it's not 0 plus or minus epsilon. It's either 0 or 1. It's binary.
Yes, but it corresponds to a measurement between.
But you don't need to know about anything like that. I mean, Bell inequality is formulated with bits of inputs and bits of outputs. The output could be a color or a smell or whatever, it doesn't matter.
But it's based on a measurement of a correlation of spin.
So I can formulate Bell inequality completely independently of quantum physics. Bell inequality has nothing to do with quantum physics.
Well,
This is a violation of it, which is coming from quantum physics, but the Bell inequality itself has nothing to do with quantum.
But what I'm sure the Bell inequality, but what I'm trying to explain is why this theory can be consistent with quantum theory, the predictions of quantum theory, without violating realism or local causality. The basic point is, the basic point is this, that, and it's very similar to what I had before, that if you have these three orientations, let's call them A, B, and C, which I just draw in general on a triangle, as before, the theory predicts as exactly would be consistent with quantum theory, that these correlations are given by the cosine of the sides of this triangle, so cosine AB or cosine AC. And this is a result, this is just spherical trigonometry. But basically what this can be shown to show is that if these two cosines are rational, so this term is certainly rational, this term will be irrational, and if you add a rational to an irrational, you get an irrational. So that the theory does not, the theory, this equation is not violated in the theory, it's just that the three terms are not all definable. So you can't say that the inequality is satisfied, because if these two terms are defined, then this term is undefined, or if these two terms are undefined, sorry, these two terms are defined, then that's undefined. And I could do a similar thing for CHSH, but it becomes more complicated because then there are sort of two triangles here, but the same logic basically applies. So well, okay, that's that. And it's the same kind of argument as before, because you can frame it in a hidden variable way by saying lambda is lambda naught if those two cosines are rational. So that will correspond to an experiment where you measure A, B, and BC. This one with those triangles. But you can't get a state on the invariant set where all three of these cosines are rational. You can only get two of them. And if you keep lambda naught fixed and measure, let's say, so if you've got cosine theta AB rational and cosine BC rational, and then try to measure with respect to AC, because that can't be rational, it takes you off this invariant set. Anyway, that's a sort of very simple. It's easier really just to think of the momentum and position, because it's an easier conception, I think.
Nick, do you have another question?
Yeah, maybe it does follow up from what was just said. How important? I'm just trying to figure out how important. I mean, the assumption that the probabilities are rational is clearly very important.
Yes.
But I'm just kind of trying to figure out where it's coming from and whether it's coming from the right place to do the work that you want. I mean, I can imagine a world in which I repeated the experiment. Hold on, that's better. Sort of countably, countably many times, infinitely many times, and so it never settled on a rational number. But really, I'd want to think of the probability as being a real number, the sort of limit I was approaching from the results of my experiment.
Yes. So, okay.
Somehow that to say that the frequencies, I guess at any time are rational, but they don't have to be if it goes on forever, there's no rational number to which I ever ultimately want to assign it, and I might have theoretical reasons for thinking there was in fact, it was tending to, the limit of these experiments was tending towards some real number. Why do you want to rule that out? I mean, what grounds can you really rule that out?
Yeah, because the basis of my model, as I say, are these fractal attractors. Now, the simplest type of fractal is the Cantor. If you just take, so the simplest type of fractal is a Cantor, what's called a Cantor ternary set. So you take the unit interval between 0 and 1 and divide it into 3 parts, and you throw away the middle part, so you have 2 parts left, and then you subdivide those 2 parts into 3 and throw away the middle part. And so you keep, in this process, you keep repeating that, but there's a basic multiplicity of 2. You have these 2 bits, 2 parts rather, two subintervals. you divide those into 2 subintervals, you divide those into 2 subintervals, blah, blah, blah. Now you can generalize that, and the whole, by the way, yeah, so the whole, the word p of p-adic, p is generally taken to be a prime number in mathematics. It doesn't actually have to be a prime number, but the algebraic properties of these p-adics are simpler if it's a prime number. But actually, fundamentally, it's an integer. And the correspondence to the Cantor sets in the case of a more general value of p than 2 is where you take the unit interval and split it up into p. Split it up into 2. Is it 2p minus 1? Sorry, I can't think on my head now. You split it up into sufficiently many intervals such that when you throw away every other interval, you're left with p remaining parts, and then you split that p up into lots of intervals and throw away every other part, and you're left with p remaining parts. So the multiplicativeness is p rather than 2. But fundamentally, and just to be technical about it, then what you're actually, the so-called p-adic integers are the set of p-adic integers are homeomorphic to that p-element Cantor set, where instead of having two parts, you have p parts. But there's an absolute fundamental issue here that p has to be, I mean, it can be a prime number, but fundamentally it has to be a finite integer. The whole theory only works if p is a finite integer. So it can be as big as you like, but it mustn't be infinite. All the properties of these p-adics just would be rendered irrelevant if you set p equals to infinity. Actually, interestingly, the real numbers, again, are an example of a singular limit of p-adics as p goes to infinity. But it's better just to think of p as a finite number, which can be as big as you like, but it mustn't be infinite. The theory won't work if p is infinite. And by the way, fractals provide a very natural way of reconciling the notion of probability and frequency. This is something I read a lot in David Wallace's book, this sort of problem of how do you, in physics, how do you reconcile probability and frequency? This is done very simply in fractal geometry, actually. But to answer your question, absolutely fundamentally, you have to be dealing with finite integers. So in the case I showed, the geometric case I showed this kind of coarse-grained trajectory, but then wrapped on it, at a finer scale, it's actually made of these little helical, small-scale trajectories which kind of wrap round. But absolutely fundamentally, there has to be only a finite number of these fine-scale trajectories. It can be as big a number as you like, but it must be finite. The theory would not work if you set that number to infinity. So because of that, that's fundamentally where this rational assumption comes, because you're taking these fine-scale trajectories, and during this period of decoherence, they separate out. You lose the helical structure, and they separate out into a discrete number of clusters in state space, which you would call in quantum theory measurement eigenstates. And you have it, so you start with a finite number, and they split into two subsets, which are subsets, so a subset of the finite number goes to one cluster, a subset of the finite number goes to another cluster. So the probability of going to one of those clusters is necessarily rational, it has to be rational. So the answer is, none of the theory works if it's not rational, and it's ultimately to do with the fact that in p-adic number theory, p must be a finite integer. I'm trying to argue here, you see, I know, you're...
So that wasn't quite, okay, that wasn't the kind of answer I was expecting. I may have answered the question, but so I wasn't thinking about there being more sort of possible outcomes. I was just imagining, I just repeat a spin-up-down experiment. Some of the time I get up, and some of the time I get down, but this experiment's going to be repeated infinitely many times. Of course, at any
is that, okay, so what I'm saying is that in this fractal space, this fractal structure, I can directly relate frequency of occurrence in the sense that you've described it, to the probability of occurrence, where probability, the word probability is exploring the structure of state space in the neighborhood of the the actual world. But that correspondence is only possible if I'm talking about frequency, because the probabilities are necessarily, as I say, for reasons I've just said, they're based on finite frequentism, so the probabilities have to be rational. So they only correspond to frequencies in situations where I'm talking about a finite sample of say experiments. So I don't know. I mean, you talk about infinite, but I think it's I think there are some subtleties here in going to the infinite limit, which maybe I mean, in ordinary everyday mathematics we don't worry too much about, but I think there are some subtleties here which you do have to worry about. So I would say to keep away from talking about infinite frequencies over infinite periods of time. But as I say, fundamentally, the answer comes from the finite structure of these fractal geometries at any iteration, that there are only a p of these pieces. There are p pieces at any iteration. That keeps repeating indefinitely, but it's the finite p that's the crucial point.
So could you just I don't want to finish, but could you then just say, look, if your theory is right, even if you could have an infinite series of experiments like that, it just would have to be a rational number. That's just a consequence of the theory.
The probability has to be a rational number. And it doesn't make sense to talk about the probabilities being anything other than a rational number because they're based on this fractal structure. The frequencies, if you go to the infinite limit, then they can become irrational. But
I mean, in principle, but it would just not be possible according to the theory.
Well, I mean,
presumably, with probability 1, they would have to agree with the frequencies would have to agree with the probabilities in that case.
Yes. I mean, my claim about being able to, let's say, evade the Bell inequality is based on this probabilistic structure, this fractal structure in state space, which is finite, and therefore the probabilities must be rational. And as I say, the beautiful, I mean, I find this, maybe nobody else does, but I find it very compelling. Quantum physics is based on complex Hilbert vectors. And it's the way in which this rationality condition comes in a completely incompatible way through the trigonometric amplitudes, the cosine theta over 2 amplitudes on the one hand, and the complex amplitudes e to the I phi on the other hand. This, by the way, exploits, I think, a property of, which maybe gets slightly to Nicholas's point. This exploits a property of trigonometric functions, which is their sort of transcendentalness. So if the trigonometric functions were just polynomial functions of theta rather than transcendental, then this incommensurateness would not actually apply, and the theory wouldn't work. So there is something actually about the Cyrelson bound in Bell theorem which I haven't quite got my head around, which does make essential. Which in my interpretation, the notion that the trigonometric functions are not polynomial actually is somehow a deep property.
Okay, I'm afraid we have to stop here. So please join me in thanking the speaker again.